slope field, here's the really good news. It's like a nice little sunny day. We're going to do art in the park. We're going to be drawing pictures today. All you have to understand is what a derivative tells you about a slope. Hopefully you understand that. And we're going to tie that into the differential equations that we did last time. So if you are looking on your notes on page 83, you see some pictures that look something like this. There's some other ones. We're going to talk about where those come from, what they mean. So example 1 has a picture. I'm actually going to create it to show you where it comes from. Example 1 has this equation in it, and then there's a picture that goes with it. So if you recall, last time we were looking at differential equations, and on today's quiz, we had a differential equation, and we were given functions, and we knew how to check to see if they were solutions. So if I asked you to check is y equals x squared a solution to this, we would plug in the derivative and the function and see if it works. Right? So we knew what to do, how to check to see if functions were solutions. What we're doing today is we're graphically drawing the solutions. We may not know what the function is. For all we know, the function could be ln x plus the square root of x, something like that. We may not know what it's written out to be in terms of symbols, but we'll be able to draw a solution. That's the goal of slope fields and direction fields. And then next time we'll actually learn how to solve them. All right, so the first one says, here's this equation, and it says on the left, which is going to be what I'm about to draw there, is a direction field showing the slopes at various points. So what I want to do is show you what we mean. Points are just points that you know from your algebra past, right? Here's the point 1, 1. Here's the point negative 1, negative 2. Right? We're talking about x, y pairs. We're doing art. So what I want to do is I want to make a little table of some points and the derivative that would make that true. And the derivative that would make that true. When I say make that true, it means satisfy this equation. And this is just like when you learned how to graph way back when in your algebra. You can pick any numbers you want, plug them in, find the corresponding y's, and plot points. So we're plotting points, but we're including the slope with our points, which I'm about to show you. I like to start with a table. A lot of you, when you go to create your own later, will kind of just find the points and put them on there simultaneously. I don't need to see your table, but I'm going to do it now to make sure you see where everything's coming from. So let's just pick some points that are within this scale. The x's are between negative 2 and 2, and the y's are between negative 2 and 2. Somebody give me a point there. Any point.
0, 0.
0, 0. I like that one. So using this equation, what's y prime? 0 plus 0. 0. That's easy, right? We're just plugging them in and getting the derivative. Let's pick another point.
1 and 1.
1, 1. If I plug in 1 and 1, my slope will be 2. Everyone okay with where I'm getting these numbers? We're just randomly picking any xy pairs, finding the slope based on the formula we were given. Let's do 2 and 2. Slope will be 4. Those are all in the first quadrant. Let's get a little more creative with our points.
Negative 1, negative 2.
Negative 1, negative 2. That was real creative. I like it. And based on this, we're just adding the x and y's to get our slope, so the slope will be negative 3. Negative 1, positive 1. Slope will be 0. Let's do a couple more. Who else want to try? Did you say 1, negative 2, Joseph? 1, negative 2. Slope will be negative 1. Can you give me another pair where the slope comes out negative? I want it to fit on the scale, though. You're right, though. I want to be able to draw it there.
-2, 1.
Negative 2, 1, is that what I heard?
Yeah.
So that's negative 1. And how about another one where the slope turns out to be 0?
1, negative 1.
1, negative 1? 0, 0 we already got. Okay, so here's some points. There's more we could do. We've just done some of them. Everyone all right what we were doing now? So here's what we're gonna do. We're going to plot points, just like we did back in algebra, like I plotted this point and I plotted this point, right? And I'm gonna use those 2 points that I started with there. But when we plot those points, we're going to draw a short little line that has the appropriate slope. Appropriate slope. So for example, at the point 1, 1, the slope is 2. So a slope of 1 is kind of the straight like y equals x. So the slope of 2 is going to be a little bit steeper, something like that. So right there at that point, I'm going to put a little line that has a little bit steeper than 45 degrees. So there's a slope that I'm calling 2. It's a short little line that has a slope of about 2. At this point, 1, 1 has a slope of about 2. Everyone okay what I mean by that? Where's the other one I did? -1, -2. Do I have that one up here? Oh, I do. -1, -2. Slope is -3. So if the slope is negative, that tells me the line's going down. And it should be even steeper than this one, because this was a slope of 2. So it should be going down through there, even steeper than that one, so maybe it's like this. Hopefully that's steeper. All right there? We're going to be doing this on your own pretty soon. Well, like I said, art in the park today, or art in the room 6. Pretend it's a park. See all the green trees around? So I'm going to put some more in there. At 0, 0, at this point the slope is 0. What kind of line has a 0 slope?
Horizontal.
Horizontal. So I have a little horizontal here. Just a little short horizontal at 0, 0. I already did 1, 1. At 2, 2, the slope is 4. So by the time I get up here, I need a really steep line. It's not vertical, but it's definitely steeper than that one and steeper than that one. When you go to draw these, by the way, I'm not going to go measure to see if the slope is really 4, but make sure that they are relative to each other. If this has a slope of 2, a slope of 4 better be steeper, right? And it better be steeper than a slope of 3. -1, -2, we did that one. -1, 1. So right here we have a slope of 0. 1, -2. 1, -2. Just turned around. The slope was -1. So that's like a 45-degree going down. So this is already on your graph. I just want to make sure you see where it's coming from, what it represents. So the little graph that you have in the upper left-hand corner of your page, on page 83, I'm kind of recreating little parts of that. I have hardly any of them in there so far, because there's like 100 of them in there. Where did I leave off? 1, -2. -2, 1. So over here, I have the same thing, a slope of -1. At -2, 1, and at 1, -1. 1, -1, the slope is also 0. So those are just the ones from my table. I think I've got them all up there. So imagine if I hadn't given you the whole thing on the page, because pretty soon I'm not, and you wanted to do the rest of it and fill it in. What do you think the most efficient way to do that would be? I mean, we could make a longer table, but I'm not sure that's the most efficient. What do you think would be a more efficient way to find those values? I'll take suggestions.
Could you set the derivative equal to like -1 and then just all the x's and y's will be equal to
Exactly. So do you hear what he said? He says maybe we'll just set the derivative equal to something like -1 and find all the xy pairs that will make it -1. Let's think about that. That's exactly what I wanted. So if we want y prime to be 1, we want to list all the xy's that would make that turn out to be 1. So let's just think about what they would be. Can you list some of them? Do we have any yet? Well, we don't have any yet.
0, 1.
0, 1. Oops, I've switched to green. That's okay. 1, 0.
2, -1.
2, -1.
-1, 2.
-1, 2. Okay, let's just stop there for now. There's some of them. Watch where they are on my graph. So if I start at 0, 1, I'm right here, 0, 1, draw a slope of 1. The next one is at 1, 0. Right here, 1, 0, a slope of 1, 45-degree angle. 2, negative 1 is down here. Do you see where those all are? They all kind of follow this little path right here. Everything right here is where they all are. I also have negative 1, 2, it's up here. I'm going to draw it real faint. If you imagine this little line right through here, this line is not part of the graph, I just want you to see it. If you imagine that blue line, do you agree that every point on that line has a slope of 1? Here's how we know. If we take this and just put 1 in there, 1 equals x plus y equals negative x plus 1, the equation of a line. That's my blue line, right? So everywhere on that blue line, the slope has to be 1. Once I know that, I can come along here, put a whole bunch more on here. Look how many more I can put on here. Just follow that line and always have that same slope. So I'm even doing the points in between, like, at negative, at 3/4 and 1/4, or whatever it might be, right? They're all on there. So you can get a whole bunch more in there when you look for those patterns. What about when the slope is 0? Say it out louder, please.
You set y prime equal to 0.
Set y prime equal to 0. So if I want y prime equal to 0, then I have, that's a prime. That was a weird little symbol. Then I have that x plus y equals 0, or y equals negative x, which is the line that goes through the origin with a slope of negative 1. So I could follow this little line right here, this little line here. If I follow that line, everywhere on that line, I'll have a slope of 0. So I could just come along and say, okay, these are all going to be horizontal, all the way along here. And then you can kind of start to see the pattern. What do you think is going to happen on all of these over here? Same thing, they're all going to have a slope of 2. Everything on that line will have a slope of 2. So I had this one already drawn. So again, I can just keep drawing that same slope as I follow that way, trying to, my best I can. I'm getting a little sloppy as I go. I meant to should have been right through there. What do you think is going to happen when I go one more up? What do you mean by same? They're all going to be the same, but what are they going to be compared to these? Steeper. So if I go up here, the further up I go, the steeper they get. The next line they'll all have a slope of 3. The next line they'll all have a slope of 4. What happens if I go the other way? Then they start going negative, right? So these will all have negative 1s. These will all have negative 2s. So then we can easily kind of just follow along, trying to make these all the same here. These are all negative 1s. Right, and then these are all negative 2s. They get steeper as I go. Trying to get sloppier as I go. And then they get steeper. And you can see, it's prettier on your page, right? But you can kind of see what it's doing from there, roughly. So this is what we call a slope field or a direction field. It kind of says, okay, any solution to this differential equation is going to follow these lines. It's going to go in these directions. I'm going to put a couple more up here just so we have them up here. So these are a little bit steeper here. These are even steeper, more so roughly there. Horrible, messy picture. Any questions about how you would create this on your own, besides taking a lot of time, which I'm going to give you time to do those? If you had the time, you sure you would know what to do? Okay, so now we want to actually talk about, okay, if there's a slope field, it represents this differential equation. Where are the solutions? Like, what's the function that's the solution? So any function is going to follow that slope field. So if you look at the second part of the question, it says example 1. On the left is the direction field or the slope field. This is the one that's on the left. On the right, they have a specific graph that satisfies f of 0 equals 1. So I'm going to add that in here. That's just old algebra information. When x equals 0, y equals 1. So that means it goes through this point right here. This point for sure is part of my solution. And now what I need to do is follow my lines. I like to call it driving within the lanes. I have to start going away at points, but stay in the lanes, don't go out. So it tells me to start going this way. And then as I get here, I have to now turn and get steeper. And as I turn over here, I have to get steeper, and I end up going like that. See what I'm just kind of following. Every time I get to a new line that points a different direction, I turn. If I come this way, it's telling me to come down. But once I get here, I'm flat. And then what happens?
It curves back up.
It curves back up because I got to kind of follow these lines. So it does something like this. So that's the one that they have drawn there. Well, theirs is drawn much better than mine because I use a computer to generate it. That shows you one particular solution. Remember last time we had an infinite number of solutions, all depending on what the constant was. We had to solve for C. This is one of the solutions that goes through that point. So I don't know what this function is. It's y equals some function. I don't know how to write it out, but I can visually see that it's a solution to this system. Let's throw another one on there that's not on listed on your notes. What if I had one that goes through, I don't know, f of 0 equals 0? It goes through that point. So it starts at 0, 0, goes through this point. And then if I go right first, I'm going to start off going directly to the right because that's the direction it's pointing. But then I have to turn and go up, and then I have to turn and get steeper, and every time I turn, it just keeps getting steeper. So it does the same thing like the other one did over there. Ooh, what happens when I go left on this one?
Pretty flat, so it's gonna curve.
Could say again?
Pretty flat, so it's gonna start curving back.
I start flat, and then I start curving up again to follow these, and then I have to kind of follow those, and I'm just kind of stuck going up again, like something like that. So those are two different solutions to the same equation. Are there any that are going to not go up there? Are they up? Can I have any down below the x-axis that stay down below the x-axis? Need another color to ask that question. Do black one. Somebody give me a point that you want to start at that you think might stay below the x-axis.
Negative 1, negative 1.
Negative 2, 0, I heard. I'll hear yours in a second, Mike, but I heard his first. Negative 2, 0, he says. So negative 2, 0 is right here. If I start off going right, I'm already going down really steep, right? And then I have to go up here, and then it's turning me this way, and then see this line here where they're, the y equals x line, this 45-degree line doesn't quite go. And actually, if I could go off my page, it's going to start hugging this one that goes up 45 degrees out. So it does go above there, but it doesn't really get flat. It just kind of starts over there and stays that way. It doesn't ever reach where the zeros are. All of them over here, as soon as they touch this point, that's where they're going to bottom out and turn around and go back up. Right? But if we can avoid that line, then we won't get those little parabola-looking shapes. Questions on either how to create it or what those pictures mean? This is why you didn't do so well in 7th grade art. Became a math teacher instead. You could create those if you had to? Okay. So example 2 gives you a definition of what we call an equilibrium solution. Equilibrium solutions are in addition to anything fancy, fancy being, you know, a graph that might look like this or like this, or which have an equation that's a little bit messier than a constant. That particular one doesn't have any equilibrium solution, but an equilibrium solution is some solution where you say y equals a constant, like y equals 5, which is a horizontal line. Any horizontal line is an equilibrium solution. So this was the slope field that they gave you. I tried to recreate it for you for example 2. It's actually for the inverse tan, this function here. Let me write out the equation here, so Nick can get that. The differential equation is that y prime equals, oh, it's just tangent, inverse tangent, excuse me. Let me think backwards it is. Y prime equals tangent of 1/2 pi y, that's the differential equation. Again, we're not solving it. But what's an equilibrium solution? A solution where you give me y equals a constant and it never moves off of there. Y equals what constant? Excuse me, y equals 2? Y equals 2, because if I start at y equals 2 and I follow it, I'm just going to go directly, oops, it's supposed to be a straight line, sorry, I wiggled. Directly left and right. Y equals 2 is an equilibrium solution. What's the derivative of y equals 2?
Zero.
Derivative. I'm just checking to make sure it really satisfies my equation. Derivative is 0, right? Does it make that true? Let's check. Is it true that y prime then equals the tangent of 1/2 pi y? Question mark, right? We're checking to see if it satisfies our equation. Well, we said the derivative was 0. If we put 2 in there, we're gonna get the tangent of pi. Guess the tangent of pi is 0. So it satisfies our equation. So y equals 2 is one of our equilibrium solutions. What's another one?
4.
Y equals 4, another horizontal line up there. What's another one? Y equals 0, down here you can see it there. You can't actually see the horizontal lines because they're on the axis, but by following that pattern you can see it would come right there. Because tangent of 0 is 0. Without seeing the rest of the graph, can you see the rest of the equilibrium solutions? Where are the rest of them going to be? Every 2, right? Multiples of 2, even numbers. So 2, 4, 6, 8, 10, -2, -4. So in general, for this case, we would say y equals 2 times any constant, where k is an integer. So 2 times 5 would be 10, that would be one of them. 2 times -3 would be -6, that would be one of them. This is all of them. The ones that we're looking at right here would just be those 3 though. Again, they would just be asking us to draw them right now. These 3, this one, and this one, are the 3 that we can see. Rough sketch, hard for me to follow my lines. Everyone all right with equilibrium solutions? The tricky thing about equilibrium solutions is when we go to learn how to solve these next time, you'll do all this messy calculus to solve for some horrendous function, which works. But also you'll have some equilibrium solutions which are just constants, the trivial solutions that you have to pay attention to. We'll be talking about that more next time. Okay, so let's do example 3. And I want you to try to create that direction field. So example 3 is a direction field for dy dx equals 2y. Remember dy dx is another way of saying y prime? So if you want to rewrite it, you can. So take like 5, maybe 10 minutes, see if you can draw that. Everyone know how to start?
Make a table.
Make a table maybe, a good idea. Look for patterns. Try it, ask your neighbor, ask me for help. Try to draw me a slope field. Oops, I forgot to put the 3 up here. Draw a slope field for that one. I'll put mine up there in a little bit. Or I'll give you enough time to be artistic. So I made a little table here, actually kind of a big table. I made my own table and I deliberately picked, I always just picked x equals 0. And I put in pretty much every y I could between here and here without doing too many. Turned out it didn't, a lot of people say, well, what do you mean put x in there, Jill? I don't care if x isn't in the equation, x is on here, so x has to be there. You have to have points. So if I was to draw these points and put these slopes in, at 0, 0 it's horizontal, so it's looking like this. And at 0, 1/2 the slope is 1. And at 0, 1 the slope is 2. And as I go up, they just keep getting steeper. Right, so the slope of 1, 2, 3, and 4. As I go down, they do the same thing, but they get steeper but more negative. So I'm up to here now, so 0, negative 1/2, 0, negative 1, negative 1.5, and negative 2. Little rough sketches of it, mind you. So those happen to be the points that I chose. And a lot of you were discussing it with each other and with me, and it was making you uncomfortable that x wasn't in that equation. But that actually makes it a lot easier. Because it says it doesn't matter what x is. The slope is always the same if you know your y value. So right here, the y value is 0. And that's true anywhere on this line. The y value is 0. It doesn't matter what x is. So this line has just a whole bunch of little short horizontal lines on it. Every particular spot here, the y values are all 0, so the slopes are all 0. Similarly, right here, when y equals 1/2, doesn't matter what x is. If y is up at 1/2, all the slopes are the same. So I'm going to draw this same little slope, trying to make these all parallel as I go across here. Trying. Those are all the same. Should be all the same. And then these are all the same, but they're a little bit steeper. Whoops, having a hard time making them the same. Doing my best. If I slowed down, they'd be better. And then these are all the same, and they're a little bit steeper. I'm gonna run out of room here. And these are all the same, and they're even steeper. And this is where some of us were going, wait a minute. Technically, they should keep going down, but I was getting a little lazy. As I go across, will you keep doing them? And if we needed to draw something over here, I could. I mean, I could spend the time putting them all in here. We could do that. And then these are all going to be negative going across here. And the same slope as I move horizontally. Most of you guys checking your work have the right picture. And these are all the same slope as I move horizontally. Helps to put them closer together, I think, to make them look the same. I spread them out and I start getting this one. And then these get steeper. And then as I move down, they get even steeper. One more down there. Something roughly like that. So my first question for you is, are there any equilibrium solutions on this one?
0.
Y equals 0 is the equilibrium solution, right? Because if I start with a y value of 0 and I try to draw the graph, it's just going to stay right there on the horizontal line. Are there any more equilibrium solutions? Higher up, lower down? Some of you are shaking your heads no. Why not? Maybe? Is that what you said? So the question would be, where would I have to go to find some more horizontal lines? Up, down, both? Both ways? What happens as I go further and further up though? The slope keeps getting bigger and bigger and bigger. Right, there's a slope of 1, 2, 3, and 4. If I keep going up, am I getting closer to 0? No, so there isn't going to be another equilibrium up here. They're just going to keep getting steeper up there. Same thing down here. The more I go down, the steeper they're going to get. They're getting closer to vertical, but nowhere near 0. So this is the only equilibrium solution. What about a solution that goes through, that makes this true? A solution that goes through f of 2 equals 1. What would that solution look like? I have my scale on here, so I'm going to put my 1s and my 2s in. Roughly this. F of 2 equals 1. Where would that solution go? Yeah, you're pointing out to the right. So it would start over here at 2, 1. I'm already off the edge. So it's pointing this way for sure. And what's gonna happen as I move that way? It's gonna get steeper, right? As soon as I go up, it's gonna get steeper. So it's gonna do probably something like this. Right? The further up I get, the steeper it gets. And to follow it down, I'm getting flatter and flatter. And look, I got totally flat right there. And if I follow it here, what happens? It just stays flat. So it actually, what's going to happen, it looks like it touches there, I should probably fix that, is it approaches that but doesn't touch it. It looks more like it's approaching it. It just keeps getting flatter and flatter and flatter and never totally gets there. What would we call that x-axis then? An asymptote? An asymptote? What about the one that goes through 0, 1? What about the one that goes through f of 0 equals what? This guy right here. It does the same thing, right? If I go to the right, it kind of goes up and does that. And as I go down, it kind of does that. Imagine if I just gave you that blue line, that blue graph that said, hey, you recognize this function? Do you recognize a function that goes through 0, 1 and has that shape? Got one person nodding. Yeah, Sebastian? Change your mind?
No, I thought you put that 0 to 2.
No, I put it through 0, 1. What kind of functions have that shape? Go through 0, 1. A to the x or e to the x? Y equals e to the x or y equals any base to the x really would go through 0, 1. Do either of those satisfy my differential equation though? What's y prime in this case? E to the x. That's not 2 times my function. Derivative of this one is even messier. This is natural log of a times a to the x, which is not 2 times my function. So we're close though. What kind of function, what would I have to do to take the derivative and end up with a 2 in front of it? What would have to be going on there? If I had a 1/2, oh, have it squared, that's the part I'm looking
Yes, I'm
for.
saying, so like with this one, for example, it'd be 1/2 y squared. No, just kidding.
Square that side. Square the e to the x, which would make it e to the 2x. What's the derivative of y equals e to the 2x? 2 e to the 2x, right? Chain rule? Which happens to be 2 times my original function. So this is the actual equation for this solution. Now, right now, we're just recognizing it. We're going to learn how to solve for it next time. But the whole point is these solutions do have equations. Some of them you can solve for easily, some we can do by what we recognize. This one just got shifted over. But pretty much exponentials are functions that when you take their derivatives, you get the same function back with some constants in front. So anything like that you can expect to look like an exponential. Questions on that one? Okay, let's go ahead and take our break here. Take a break now, take a 10-minute break. I'll show you how the computer, Desmos, can generate nice slope fields for us. And then we'll do a couple more by hand, make sure we got this down. So example 4 is kind of a weird one. It's not as straightforward as the 2y that we just did. Both example 4 and example 5 are a little bit strange. So let's have you guys get started on example 4 without me again, and then I'll fill mine in a little bit. Example 4 looks like dy y dx equals x minus y. And then we're gonna sketch equilibrium solutions through both of these points. So take 5+ minutes and see if you can get the slope field for this one. It's not as easy as the last one, but it's kind of familiar. See what you can do with that. You can find the pattern there. So I started with, okay, let's talk about all the points that will give me a slope of 0. So I just started listing points that I knew would give me, oops, I did not list, I was doing the wrong one. Hang on, let me erase these. I was looking at the first example when I did this, so that's good. I want to list a bunch of x, y's that when I plug them in there will give me a slope of 0. So give me some x, y pairs. Basically, I need two numbers that when I subtract them, I'll get 0. So it's going to have to be numbers that are the same, right? 1, 1, 2, 2, -1, -1, -2, -2. It's kind of quick to come up with all the ones that when you subtract them, you'll get 0. So I like to do those first. All of these are going to have the same slope. They're all going to have a little horizontal line. So if I start there, I come over here. Let me grab another color. Put it in red this time. I know at 0, 0, I'm there. At 1, 1. A lot of you started there. I noticed that. 2, 2. My scale's not really good right now, but it's close enough. So I can kind of get those in there. And then I can see that in between there, if I follow that, I'm going to have the same. So I kind of add some more in between. So that's a quick way to get a lot of them done. And then I want to think, okay, now give me some x, y pairs where the answer will be 1. So I just need some x and y's so that when I subtract them, the answer is 1. And so I'm just going to pick some x's that are 1 more than a y value. Maybe 1, 0. Right, that's 1 more, so when I subtract them, maybe 2, 1. See what I'm doing there? I'm just trying to subtract, find some numbers that when I subtract them, the answer will be 1. What else?
3, 2.
3, 2, so that's off my scale. I agree with you. 3, 2 works. Can I do some negative values? What if x is 0?
-1.
-1, right? If I subtract those. Or if x is, say, -1,
-2.
-2. So I picked some of those. Just trying to subtract them and make them come out to be 1. Then I know that all of those have a slope of 1. So I'm going to come over here. At 1, 0, I have a slope of 1. And at 2, 1, I have a slope of 1. And at 0, -1. And at -1, -2. And then I notice that those all follow that line, so again, I fill these in along there. Over here too. A little bit quicker way to get a bunch of them done, because if you made a table, that's like 20 points on the table right there. How about ones whose slope is 2? Give me some points where the slope will be 2.
4 minus
2, 0.
2, 0, what'd you say, Carlos?
4 minus 2.
4 and 2, but then 4 is off my scale, so I won't be able to fit it on there. But you're right, 4 and 2 would work.
1 and -1.
1 and -1,
0,
0,
-2.
-2. Just picking some where when you subtract them, you'll get 2. This one has to be 2 more than that one. So now I come over here at 2, 0. Now I have a little bit steeper slope at 2, 0. And also at 1, -1. And also at 0, -2. And then because those I can see all follow this line, I'm going to try to do those same slopes moving along there, roughly. And then we can keep going. We can say, okay, now which ones are going to give me a -1? And we would have to pick x's that are 1 less than the y's, so when I subtract it, I'd get -1. So maybe 0, 1. 1, 2. But if you look for these patterns, it just makes life a lot easier. There's some more in here also. What would I have? -1, -2. Oh, -1. Hang on. -1, 0. There we go. Where do those fall into my picture? What'd you say? Yeah, on the left, but some of them are on the right, like 1, 2 is on the right also. But where are they compared to what I have so far? 0, 1 is here, 1, 2 is here, the other one's over here. It's basically following the next line up essentially, that next diagonal line up. Those all have a negative slope. So I should be following this, drawing my negative slopes along here. What's gonna happen if I go up another diagonal line?
Everything more negative.
They're gonna get more negative, but still follow that same pattern. So these will get steeper but more negative, steeper but more negative. And same if I keep going down this way. So I'm gonna show you what it looks like on the computer, because it's faster than me finishing it. See if your picture looks like mine. You can get this one, Nick. Finish it off. Should look something like, after it starts up. It's so much prettier when you see it all done than when you try to create it. You can see the swirls better. I still don't know how to get rid of that. This button doesn't want me to escape. I don't have an escape button. The last time it went away of its own. Okay, so it should look something like this. Here's all those horizontal ones that we did. Here's all of the ones that have the slope of, where did they go? Slope of 1. All these along here, all these have a slope of 2, so forth, as we moved away. Yours looks something like that. And finish mine over there on the left. So once it's done, you can kind of see where the direction it's going a little bit better. And some of us are better artists than others, and the computer's obviously prettier than that. So that's what that final one looked like. We wanted the solution through 0, 0. Well, like that one automatically went through 0, 0. So through 0, 0, if I start at 0, 0 and I follow these lines, it kind of forces me to go follow this way. And then if I follow these, I end up going that way. And what was the other one? 0, 2? Or 2, 0? I can't see it from here.
0, 2.
0, 2. So if I move this up to 0, 2, it looks something like that. Does this look familiar to you? From today? Does it look familiar from what we've been doing today? Like one of the examples we did earlier. Which example does it look like? Example 1. It's almost identical to example 1. The very first example that we did. What's the difference? It's flipped. So example 1, if you go back and look, example 1 had almost the same shape, but we had them going off the following that way to this, where they don't really intersect, but where they end up on an asymptote. It was essentially just flipped, where what's going to the left was going to the right on the other one. We had diagonals going the other way on example 1. What's the difference in those equations? X plus y and x minus y. So this was example 4 that we're doing right now. Example 1 was y prime equals x plus y. So really the only difference is this. Your y's are going positive or negative, which is why example 1, all of our diagonals were going this way, and now they're just going that way. Positive slopes versus negative slopes. It's almost identical that way. Everyone clear on how you would draw these on your own, the green ones? Like I said, just put your point and stay in the line. Follow the line. Good there? Okay, I want you guys to do the last one on your own too. One more. The last one's a little bit weirder because it's got multiplication. See what you can do with that last one? I'll write it up here on the board and then I'll fill it in a little bit. You might try my pattern that I did, maybe you won't, I don't know, the pattern's a little bit weird on this last one. So the example was it 5? Example 5 is different in that it is multiplication. dy dx equals 0.5 times x times y. See what that one's gonna look like. It's not gonna follow any lines. Why not? How do I know that? What'd you say? It's not the 1/2. It's the multiplication that does it. The multiplication makes it so it's not following line. See what you can do with that one. And I'm going to use my other technique of trying to find some XY pairs that satisfy whatever I'm looking for. I already did a shortcut and said if I want the slope to be 0, it can be anywhere on the x-axis, anywhere on the y-axis. Because as long as x is 0 or y is 0, it's going to be horizontal. So all along here, these are all horizontal because the y values are 0. And all along here, these are all horizontal because the x values are 0. Those are done quickly. Those are the easy ones. Some of you got those done real quick. And now I want to figure out some points that will give me a slope of 1. So I'm multiplying 1/2 times x times y. So what do x and y have to multiply to get me an answer of 1?
2.
Yeah, x times y has to equal 2, right? Because it'll take half of that. So I need two numbers that multiply to 2. So I could do 1 and 2 or 2 and 1. Because they multiply to 2 and half of that will be 1. So if I find those, 1, 2, and 2, 1, this has a slope of 1 right here. And 2, 1 has a slope of 1 right here. There's only 2 of them. Where would the other ones be? I don't know. Negative, like for example,
-2, -1.
yeah, -2 and -1 and -1 and -2, same thing. -2, -1, the slope of 1, and -1, -2. So at -1, -2, -2, -1. Okay, we'll see if that's enough for now. We might need more. Where would the slope be 2? I might have to go off my scale to find some of those. Couldn't hear you.
When it multiplies up to 4.
Yeah, when these two multiply out to be 4. So we could do, like 2 and 2. Right, because 2 times 2 is 4. And half of that will give me 2. So the slope is 2, which means out here it's even steeper. Where else? -2, -2, and it's still steeper here. Okay, we're getting somewhere. What about -1?
-1, 2.
-1, 2, he says. And 1 and -2. Anything that multiplies out to -2 will work, right? -1, 2 is up here. What did the slope was? -1. So it looks like this here. And 1, no, that's my place. 1, -2. So you can kind of see the pattern so far in that these are like mirror images of each other, as so are these. Whoops, -1, okay, well, that's my place. Now where was I? How about here?
-2 and 2.
-2 and 2? So So -2, +2, I have a slope of -2, so up here it's a little bit steeper, something like that. And
2, -2.
2, -2. So it's over here, it's a little bit steeper. So these guys match up, these guys match up, those two. I still feel like I have a lot missing though. Say that again?
They're not gonna be whole numbers, they're gonna be.
They're not gonna be whole numbers, but what's gonna happen, say over here at 1, 1?
Slope of 1/2.
Slope of 1/2, right? Because 1 times 1 times a half. So it's not quite as steep as that's half of it. So maybe it's a little bit flatter. At 1, 1. Same thing at -1, -1. A little bit flatter there. Same thing over here, when they're negatives, it's gonna be flatter but negative at -1, 1, and at 1, -1. Try and make those flatter. So I think we kinda have enough there. I think I missed this guy here. We could put those in there though. If something looks kinda like that. Again, we could argue on whether the table was easier or whatever, but there's no nice pattern. The pattern here is kind of these mirror images. And then we wanted to draw equilibrium solutions through 0, 0, and 1, 1. So if I want to draw, not equilibrium solution, excuse me, a solution through 0, 0, if I start at 0, 0, that is an equilibrium solution, right? Because it says go to the right, which keeps me here, and then go to the left, which keeps me there. So that one happens to be an equilibrium solution if I start at 0, 0. Did I say 1, 1? 1, 1. Here. What's that gonna look like? Kind of like a parabola, because if I come this way, it's going to start going up, right? And if I come this way, it's going to get flat here and then follow the other ones going the same way. Roughly like a parabola. It's not actually a parabola, but roughly like that. So this is the one that goes through 1, 1. This is the one through 0, 0. Are there ever going to be any down below here? Anything ever stay down below there? Yeah, can you point that it would start at to do that?
Or just leave below.
Just stay below, yes.
You can start at, 1, negative, or -1, 1.
Negative, you're pointing.
1, -1.
1, -1. So if we start at 1, -1, I added another point on here. It has me going up, but once I go up, I get flat right here. And then it has me going back down. And same thing over here. So I end up with another one down there, maybe. So we're actually going to learn in the next section how to solve this one. To find out an equation for y. Like how to get the actual equation for the function that satisfies this. Kind of like I showed you that y equals e to the 2x earlier. Let me tell you what the solution is. Sometime, next time, someone's going to remind me to show you this one if I don't remember on my own. The solution actually ends up being this. Any constant times e to the 1/4 x squared, or y equals 0, which is our equilibrium solution. This is the equilibrium. Now, you don't know how I got those yet. We're going to learn that next time. Is y equals 0 included over here? No? Question mark, he says? No? I like that. Does this include y equals 0? Why not? So it doesn't look like this?
But if you should have 0 and raise it, then the
Uh-huh.
power would be 0.
Well, and what does this say? This says any constant times this. What if I choose c to be 0? If c equals 0, it'll equal this, right? So we technically don't need to list this separately. If c equals 0, in there, we'll get y equals 0. That's the equilibrium solution. So this actually includes that. What do you think is true for this one? What kind of C do you think we have here? What can you tell me about C? Think it's positive, negative? Why do you think it's positive?
Why they see positive?
You think C is positive there? Because
I was gonna give you a question, I don't know.
you're talking to yourself?
Wait.
What kind of C value would give me this picture? Has to be positive y.
Because it looks like negative.
Right, because nothing's negative, right? All those y values are up above. So all my y values need to be positive y values. This part's already positive. This part's positive, multiplied by a positive. This looks like it goes through like, I don't know, call that 0.8. Roughly 0.8 right there. I'm estimating what that is. When I plug in x equals 0, I get 0.8. Let's see a 0.8 right there. Actually, would probably give me that green one. Approximately, I don't know, I can't tell what that number is. What do you think C is right here? Negative 0.7 maybe, or down below, not quite, somewhere between 1/2 and 1, and then C value. So what we've been doing today is drawing pictures of functions that we're going to learn to solve for next time.